Hello, everyone. This is Professor Ma, and this is the introductions on the sections on surface integrals and flux. Previous sections on surface, we introduced surface integrals through the point of views. You have a surface, a very thin, that we call a lamina, it's very thin surface. And we have density on the surface at each point, and then we want to calculate the mass of the surface. And then we wind up with the applications of the surface integral ds. Okay, now we're going to do the same things. We're going to use the surface integral ds to talk about another problem, that is the so-called flux. That is, we want to calculate uh, calculate across a surface. Think of a flow, okay, and we call it that a flux, okay. And in all the discussions, what we're going to talk about, we're going to assume the flow is a steady flow. What we meant by a steady flow is that it doesn't depend on time. That is, the flow is the same at each individual point in three-dimensional space we're talking about. So the way to think about it is when we turn the faucet, okay, and the water gush out, and after the water gush out for a while, then the flow become a constant, then they form a slight conical shapes, and then at each point inside, the flow at each locations stays the same. Okay, and because that's the case, so the whole column of water look like it's not doing anything. It looks like a block of ice, burning ice, if you will. That's a steady flow. Okay, and we want to calculate in such a flow. We have a surface sits across, and how much is flow across that surface in a given unit of time. Okay, so all the flow in these discussions are assumed to be steady flow. So we want to calculate the amount of fluid flow across a surface at one unit of time, because we have to be careful the word across here, because the surfaces that, in order to talk about across, there must be two sides. There are surfaces we cannot define having two sides. It's impossible. The Mobius strips. We'll get to it. Okay. Well, first, we define a surface. It's orientable. That is, you can choose the directions for the surface, choose sides for the surface. Is that you have you can select normal vectors, perpendicular vectors, everybody to one side, such that this vector field is continuous. And they say, what do you mean by continuous? Meaning that I think of any path I have on these surfaces, also some path on the surface. And if I were to look at all the perpendicular vectors on this path, and when I walk around the path, I wind up exactly the same vector I started out with. It doesn't matter what the path is on this surface. I can always meander, and I can take a pole, and the pole says that's up, and I walk around the surface, and I always wind up where I started, and the pole still pointing the same when I started it. If that's possible, we say this surface is orientable. Okay. Mobius strips not. If I take a pole pointing upward and start walking around outside, quote unquote outside, look like outside, and go around, that's where the pole is. But when I come to here, the Mobius strips has a twist. Okay, you take these two pieces of paper, you make a twist, and that pole, that twist, now the pole I'm holding pointing up now is pointing at the opposite direction of when I started, even though I'm standing exactly at the same point. So this is impossible. Therefore, on the Mobius strips, it's impossible to define two sides. So therefore, the questions of flowing across doesn't make sense anymore. So we don't want to deal with the flux on non-orientable surface. So we restrict our surface all to be oriented. So once we have oriented surface, I can choose, therefore, all the normal vectors, in particular uninormal vectors, to one side. Okay. And so a surface with one side chosen, okay, and we call that an oriented surface. The word oriented means you have a side, you have a preferred side for the directions chosen. Okay. And the normal vectors, okay, forms the orientations of the surface. Okay. Meaning points at the direction of the surface. So an orientable surface have two sides, got two choices. And so here we go. Flux. Oh, okay, now let's let's talk about the flow. Okay, so a flow I can represent in three-dimensional space. I can represent it by ijk component, and I can have three vector value function f, g, h for the ijk components correspondingly. Okay, so they look like a bunch of arrows in space, right, pointing in different directions. Okay, a steady flow again is that at any time this picture doesn't change. The amount of flow doesn't change. At times it's constant going across at any point. So I want to calculate now, put these two together, the surface with the orientations, with the chosen directions, plus a flow in three-dimensional space. Now we want to calculate how much is flow across the surface. Now let's suppose the surface is now described by a functions in x and y. And so here's a pictures. Okay, and let's assume n is the orientation, is the uninormal field that we chosen. Okay, and then there's a flow now in three-dimensional space, and the flow is defined by capital F. Okay, on a small patch, we can talk about the well, let me back up for a second. Okay, so we're going to calculate. So imagine now there's a flow across somewhere. There's a flow in space. There's an F over here. Okay. We want to calculate how much flow is across this small patch of pi. So this is F over here. And this small patch of pi, of course, has a normal vector n sub I. Okay. And we're going to calculate the amount of flow across that small patch by the tangent tile over the small patch. Remember that little tiles that's tangent to the surface, corresponding to the dx dy over here that sits over dx dy. Okay, we place this little patch by this tile, and these tiles came from the surface differential. ds can be expressed the area of this surface, okay, can be expressed in terms of the ds. Now, we want to calculate how much flow across this blue patch. And when the flow is in the directions of Fi. So we are going to calculate how much flow is across this tile in the direction of Fi instead. Well, the flow in the direction of Fi is a small tile, rectangular tile. If it flows across space, it forms this squashed box. It's called parallel pipette, okay? And that volume can be calculated. How? By dot product. If this is the unit normal, then the height of that box is the dot product of the force vectors at the point Fi dotted with the unit normal at the point. That will give you the height of the box. Now, how about how big is the base of the box? The base of the box is the surface differential, area of Ti. Okay, so this is the height of the box. And this is the area of Ti. And so basically I'm saying if I put this on the ground and this is a box that's tilted, but the height of this is F dotted with Ni. So all I have to do is multiply by the area of Ti. And the area of Ti is the surface differential, dx dy. So putting all these together, and we add up all the flow across each little patch, and so we wind up with this integral formula, dot product in the formula. So with F data with, and remember this is the unit normal. Okay, F is the flow, the flux vectors. N is the unit normal vectors. You want to dot the things and do all these surface differentials. Except these things actually clean up a lot further. Okay, but pause for a while before we clean it up any further. We usually, this is the surface differential. We just write as ds, and of course we're doing surface integral over the surface defined by z over sigma. Okay, so this notation you will see. But continue with simplifying. Okay. There are two unit normal. I mean, when we talk about unit normal, it's not secrets. Basically, that's the partial respect to x, partial respect to y, and you stick one in the back. For z, in the distinct z positive directions, okay, because y in the z component is pointing, sometimes we call this pointing up, so hence it's called upward because z equal to 1. Okay, this is the unit normal. And then if you switch all the sign around, it will be the opposite direction. There will be the opposite side, it will be the downward unit normal for the surface. Okay. And then, so if you, for instance, if I have the upward unit normal, then go back to this formula, you we can simplify even further because the norm of the length of the partial cancels out, and so we actually just wind up f dot with the f dot with the partial z, partial x, partial z, 1. Okay, the unit norm of the partial, the so-called the delta field. Okay, so this is the formulas I'm talking about. So, for instance, okay, so the volume total, the total amount of flow in upward directions is given by simply this formula. F is the flow fields, and this, of course, is the normal vectors defined by the partials with a z equal to 1 pointing up, and you dot these two vector fields and integrate it over the domain R. If it's downward, then you change the sign for the partials. Okay. So let's go to one calculations. Okay. So we have a surface defined by x squared plus y squared, and that's a parabolic bow. Okay, below z equal to 1, so therefore it's only the bottom. Okay, so we have that surface, and we'll have these flow fields. There's no I components, okay, only the J components, Y, the K components is a constant 1. So the flow fields in this three-dimensional space and gives you some ideas how it flows. So we want to calculate the volume of the flow across the surface. Okay, downward unit. Okay, that means I want the z component to be -1. So we want to calculate the integrand. What's the integrand? In this case, f dot width, since it's going downwards, I want this -1 zx zy and integrate over r d. This is downward. Okay. And that's the integrand. Integrate over what? Over the region R. The R is a circle here. So and then since the circle, then it's easier if we put this into polar coordinates. Okay, so r from 0 to 1, theta 0 to 2 pi, and change y to r sine theta, and dr d theta. So obtain these. Here is a problem that comes in 3 parts. 1 to 4 parts, sorry. We have a tetrahedron. And the question is how much is flow toward the outside of the tetrahedrons? Okay. So the orientation is outward. Okay. So the question is, given this float field, what's the total outward, quote unquote, outward flow? Okay. And this is where the outward, you have to use the word outward to define which directions you are flowing. So there are 4 surfaces over here. Okay. Depending on which direction they are flowing, and you have different normal the partial that you have to calculate with respect to different directions you are flowing. And this is where, let me go back up to slide. Okay, the other, they are the other surface flowing across the orientations of the surface. This the one that flows across in the positive y directions. Then you will use this as the partials, and you have to switch all the variable around. You have to calculate partial y with respect to x, respect to z, and with the chosen normal fields, the surface as this as a normal, and do the dot product in in these directions, and this is the positive y direction. If it's a negative y directions, you change the signs around. Similarly, in the x directions, okay, I guess you can say it's right and left, front and back, but it depends on how you draw your x, y, and sometimes x is front and back. So hence we orient these the directions of the surface in positive, negative of the axis directions. Okay, of the direction of the axis. So in the positive x direction and the negative x direction. Positive x direction, you will have partial respect to yz, and then the x variable is positive, pointing the same as the x directions, positive direction, then positive direction of the x, and the negative x direction pointing the same as the negative directions of the x. And these, you have to apply them to this different orientation, to this problem. Of what it means to be outward. So for instance, on the back on this, outward will be in the negative x direction. Okay. And then you have to think about what took place. Okay. Most of this come out with 0. So I'll let you to read through this example and orient yourself the outward direction correctly with the specific dot product. Okay, and that's it. Bye-bye.